I'm David Grinspoon. I'm an astrobiologist and a planetary scientist. And that may sound like what I mostly do is think about other planets, and I do work on spacecraft investigations of other planets, but a lot of it is focused on a comparison with Earth. And one of the benefits of this comparative planetology approach, as we talk about it, is new insights that we gain into our home planet. As an astrobiologist, I'm interested in the question of life elsewhere in the universe, and that also turns our lens often back to our own planet to ask questions about basic questions like what do we mean about life, and what do we mean about intelligence if we are searching for extraterrestrial intelligence? And so by trying to sort of universalize these concepts, sometimes we gain new perspective and new ways of looking at ourselves. As far as the climate challenge, I've come to see this as part of a larger set of challenges involved in recognizing that we are in a fundamentally new chapter in the history of Earth, marked by humans as a newly empowered, if somewhat confused, geological force. And my title here, Terra Sapiens, is sort of an aspirational title. It means wise Earth, and it's a title for the kind of planet and global civilization that I believe we can begin to think about creating if we recognize the true nature of our existence here on Earth. And some of that has to do with seeing how we're embedded in planetary history and recognizing the true strangeness of this current moment when humans have become a force of planetary change and trying to own up to that responsibility. So that's the basic framework for what I'm going to be talking about. A lot of this comes from a book that I wrote a few years ago called Earth in Human Hands, Shaping Our Planet's Future, where I tried to apply my perspective as an astrobiologist to this new age, the Anthropocene, that we've now entered into on our Earth. Let me say a little bit more what I mean by astrobiology and the Anthropocene. So astrobiology is kind of the scientific effort to figure out how we fit into cosmic evolution. And here's my one-page cartoon summary of the entire history of the universe, or what we call cosmic evolution, where we focus on the larger changes that the universe has gone through from the very beginning, which we call the Big Bang, to the present day. So you can see some of the highlights of this journey we've been on. After the Big Bang, there was the creation of galaxies, and within galaxies, the creation of stars, and around stars, the creation of planets. And when you had the formation of planets, you had a location where some very interesting chemistry could occur, some of which on this one planet here led to the origin of life. And then a lot of evolution occurred over billions of years, and we had the evolution of complex life and what we call civilization. You can see down in that last panel, and then it ends with question marks of what's next, because there's no reason to think that our current stage is some sort of climax or apotheosis of evolution. It continues. But what we try to do with astrobiology, in a sense, is try to understand if these last two stages you can see on this cartoon summary of the universe, the origin of life and the origin of complex life and intelligence and civilization, are those two stages common throughout the universe, or are they just unique to Earth, to the experience of Earth? We have some hints that suggest to us that the origin of life may be common elsewhere in the universe, and some ideas about the evolution of complex life and civilization elsewhere. And we're on the trail of data to try to confirm these ideas and try to really place ourselves within the story of cosmic evolution. So that's astrobiology. When I talk about the Anthropocene, I'm talking about the idea that we've entered a new stage of geological history. You can see here the geologic time scale, which you've seen. This is a cartoon version of it, but you've seen this in books and on classroom walls, where we divide up the history of the Earth into these different periods and epochs and eras and eons that we give different names to. You know, famously the Jurassic is a movie star geologic period. But most recently, we've been in the Holocene since the last ice age about 10,000 years ago. And the idea of the Anthropocene is that we've now entered a brand new geological age marked by the existence of a new geological force, which is the combined forces of humanity changing the planet. It's a bit of a controversial topic, but controversial in a good way, because it has people talking about and examining the human role on Earth. Some people are opposed to it because it seems arrogant. Why should we name a geological age after ourselves? But on the other hand, to me, it seems like a sort of owning of our responsibility, recognizing the role that we play. There's no doubt, if you just look at the numbers of what's happening on the planet, that we have become a new major force of geological change on this planet. And so recognizing that and giving it a name, the Anthropocene, can maybe help us to own it and to own up to it, and to think about what it means, that responsibility, how we need to behave on this planet, not just for our own self-interest, but for the future of our biosphere. So let's imagine now for a moment that we were extraterrestrial astrobiologists, scientists from another planet, observing our own planet over billions of years. Imagine you were a very patient extraterrestrial. So you had a long attention span. You're observing Earth for billions of years. What would you notice on our planet? Well, you'd notice the continents shifting around the planet with continental drift and plate tectonics, like a spherical morphing jigsaw puzzle, the continents coming together in supercontinents and splitting apart and sliding around the planet. You'd notice the polar caps growing and shrinking rhythmically over time through climate change as our planet went through ice ages and hothouse ages. All of these changes for billions of years you would see, but the night side of the planet for most of that time would have been an unbroken black, maybe the occasional splash of lightning, but mostly just blackness, until about 400 million years ago, when forest fires would start to appear as life came to cover the continents and the greening of the continents. But mostly for all those 4.5 billion years, an unbroken blackness at night, until very recently. Whoa, what is this? The night side lights up in a brand new pattern, sort of organic looking, but hugging the coastlines, and then strange linear patterns spreading across the continents. And at the same time as the night side of the planet lights up, you'd notice all these other new rapid changes in the geometry of land surfaces, new rectangular and circular forms, changes in the composition of the atmosphere, changes in the ocean, new strange linear clouds streaking across the sky. Something new and very strange is happening on this planet that you haven't noticed for billions of years. The night side's lit up, all these other things are happening. And then just in the last 60 years or so, something else very strange and very new. Little bits of the planet start leaping off back into space from where everything once came billions of years ago. Little metallic contraptions leaping off the planet, circling the planet, looking down, seeking information. The planet starts to be self-aware and self-observe. And then at the same time, some of these little contraptions heading out to the other planets and circling them and sending radio signals back home. This is very new and very strange. The planet is behaving in new ways. What's going on here? One species has developed curiosity, technologically enhanced curiosity, and is seeking answers to its origins and trying to understand its universe and its neighborhood. So there's one curious species. Humanity has been sending spacecraft to the other planets, and we just saw the sort of combined graph of all the spacecraft missions throughout the solar system we've sent to this date. And one point of that is the harvest of information that we can then put into this field that we call comparative planetology, where we learn more about the stories of the planets, including our own Earth, by not seeing them just in isolation, but by comparing and contrasting their stories and understanding their similarities and their differences, we start to understand how planets work in general. To give you one example of comparative planetology, these are my 3 favorite local planets, Venus, Earth, and Mars. They're all kind of fun and interesting and instructive comparisons we can make between them. And here are images of what are river deltas on all 3 planets. And you notice the similarity of form. Nature loves to repeat the same forms, even in very different situations. So a river delta is formed when you have a flowing river, and then it opens out into a larger lake or ocean, and the water slows down and drops its sediment and sort of makes this fanned out shape. So over on the left, on the bottom left, you see a river delta on Venus. And we know that that was not carved by liquid water because the surface of Venus is really, really hot, about 900 degrees Fahrenheit, and you cannot have liquid water there. So that was carved by some sort of runny magma, some melted rock flowing across the surface. And then over on the bottom right, you see there's a river delta on Mars, but if you look closely, you notice that it's an ancient feature. It's covered with some craters. It's eroded in ways that tell us that this is from flowing water that flowed into a lake, but billions of years ago. So this tells us more about the story of Mars, where there was once flowing liquid water on the surface, but that activity stopped billions of years ago. And then in the middle, of course, we see a river delta on Earth. And again, you see the same similarity of form, but if you look closely on Earth, you see the presence of biology. And indeed, biology shapes everything about Earth and defines its differences from the other planets. And in this river delta, if you study the forms closely, you see that the signs of mangrove swamps and other biological forces interacting with the flowing water to create a unique picture. So here we have the same form on all 3 planets and telling us of similarities, but telling us the unique story of each planet. One that's just been far too hot for liquid water, one where the water disappeared billions of years ago, and one where the planet has been taken over by life. Now, when we use comparative planetology to study the stories of our nearest neighbors, one thing that we do learn is that both Venus and Mars, our near neighbors, seem to have had similar origins and early environments to Earth. They both show signs that when they were young, they had a similar climate that was suitable for running water, and they both probably had liquid water oceans at a time when the origin of life was happening on Earth, dependent on the presence of liquid water oceans. So this is really interesting for astrobiologists. It seems as though our nearest neighbor planets both had conditions suitable for the origin of life, even though neither one of them seems very promising right now for life, at least on the surface of these planets. So maybe this is telling us that on rocky planets, they're often born warm and wet, and maybe they even often have an origin of life. And maybe what's rare about a planet like the Earth is that life has become a global property and has helped to keep Earth alive. Whereas on Venus and Mars, maybe you had an origin of life, but life never sort of went global and became, neither one of those planets developed the kind of global biosphere that Earth has. So when we think of Earth that way, we think of life as not just as an accident, but maybe some kind of planetary property which has taken over the planet and has helped to sort of guide its development. As one of my colleagues, as my colleague Colin Goldblatt has said, he said this at a meeting and I wrote it down because I just really liked it. The defining characteristic of Earth is planetary scale life. Earth teaches us that habitability and inhabitants are inseparable. This last sentence, what it means in terms of my field of astrobiology is you can't just go out and look for planets that have the right conditions and then say, oh, they probably have life. What you ought to do is go out and look for planets that have been transformed by life as Earth has. And that changes the way we think about life on planets, that maybe life is not just something that happened as an afterthought on a planet with the right conditions. Maybe life is a state a planet becomes alive in the sense of life being a state that the planet enters into and becomes. It's a global, a planetary property. And when we think of life that way, and then we think of the more recent evolution of the Anthropocene, see, I'm coming back to the theme here, then that makes me wonder, as we look at Earth under the influence of this new type of geological force, the global activities of humanity defining the Anthropocene, it makes me wonder, could intelligence like life become a planetary property? In other words, could it become a force that is deeply integrated into the functioning of our planet in a sustainable way that actually helps the planet remain sustainable as life became? So this is just another way I'm trying to introduce here to think about the nature of intelligence on a planet, and maybe then even the nature of humanity and what phase we may be entering into in the planet's history. So in thinking about the role of humans on Earth in this strange moment we're at, where we've somehow become agents of planetary change, I think it's important to look at the long history of the planet and to recognize that we humans are not the first species to come along and radically change the planet. We're not even the first species to change the planet in such a way that caused the mass extinction of other species. We're not even the first species to change the planet in the quest for a new energy source and pollute the atmosphere to the point of causing dangerous climate change. No, all this was done 2 billion years ago by these little guys right here in this slide, the cyanobacteria, right? They look innocent enough, don't they? But they perfected this new energy source, which was solar energy. They perfected photosynthesis. And in the process of doing that, they polluted the whole atmosphere with this dangerous new gas, oxygen, O2. Now, of course, we love oxygen, right? I know I do. It's what powers our biosphere. But when it first appeared in Earth's atmosphere, liberated by these photosynthesizers, it was a dangerous gas because oxygen reacts really intensely with organic life. And species had not evolved to handle that. And it caused mass extinction and mass climate change when the cyanobacteria polluted the atmosphere with oxygen. Now, of course, what happened next was life did what life does, which is it adapts to new changes. And in fact, those powerful reactions of oxygen with organic matter, once life learned to harness that, then new forms of life took advantage and it liberated much more energy for life to use. That's how we live. That's called respiration. We use those reactions of oxygen with organic matter. Every cell in your body has a power plant powered by those powerful chemical reactions of oxygen reacting with organic matter. So it's great when life adapts to it, but when it first came along, it caused a mass extinction. So anyways, we hear this story and we don't think, oh, those irresponsible cyanobacteria, what were they thinking? We don't think that because we know they were just bacteria and they weren't thinking anything, right? But we see ourselves behaving in an analogous fashion, and we think, well, how could we? So what's the difference between us and those cyanobacteria? We're not the first species to cause global change. So what have we got that cyanobacteria didn't? And this is where ideas of agency and intelligence and tool use and all this stuff comes in that we could talk about for a long time, which is, this question of human exceptionalism, what really is fundamentally different about us. But in the context of the Anthropocene, what I've realized in through exploring all this is that the way I would sum it up is, in terms of Earth history, we are the first geological force aware of its own existence. And that is should be empowering, but it's also kind of frightening, because it's really brand new, and we in a way we clearly have not learned how to handle this knowledge yet. But I think writ large, that's our task, is to learn how to handle this knowledge, because I think we can't go back and stop being a geological force. So we need to learn how to be a good one, a constructive one, one that is acting and operating in a way that is conducive for sustainability and for a healthy relationship with the biosphere. So In order to come to grips a little bit more with this strange new role that humans are in and contextualize that within the larger framework of planetary evolution that I operate in, I've looked at all the different categories of catastrophic change that can happen on planets. And I've decided there are 4 kinds of planetary change, and I'm going to briefly run through them for you now. And this is all in the service of putting into context the human role. Okay, so but categorized with respect to the role of life in planetary change, here are what I call the 4 kinds of planetary change, or the the 4 categories of planetary catastrophe, if you will. So 1 are just random catastrophes. This is, when bad things happen to good planets. You're just in the wrong place at the wrong time. Life has nothing to do with it. Life is an innocent bystander. So this is when an asteroid or comet hits the planet, as happened 65 million years ago and wiped out the dinosaurs and almost everyone else that was alive at that time. Or this can also be a massive volcanic eruption from the interior of the planet. The main point is here that the role of life is completely passive, has nothing to do with it, just in the wrong place at the wrong time. The second category, second kind of planetary change, are what I call biological catastrophes. And this is when the evolution of life leads to catastrophe for other species. When some species or some class of species is so successful at surviving and they spread themselves so well that they then cause environmental change, which is catastrophic for other species. So this is what I call biological catastrophe. And there are many examples in the history of the planet, but the best example is the one I already described, the evolution of green plants and how that changed the atmosphere and led to mass extinction and mass climate change, and really was a catastrophe for most of the species on the planet at that time, and is symbolized here by a green leaf. Okay, so those are planetary changes of the second kind. Now I'm going to tell you about planetary changes of the third kind and the fourth kind, and both of these are where cognitive processes come into the picture. Both the third and the fourth kind of planetary change have to do with clever species inventing things and changing the planet. And yet there's a very important distinction between the third and fourth kind of planetary change that I will try to make clear. So what I call planetary changes of the third kind are inadvertent planetary changes. This is when one species gets very clever, invents technology, so it's able to start increasingly modify the world around it, and becomes so good at solving local survival problems using this enhanced technological ability that, completely unbeknownst to themselves, they begin to cause global changes. And that last part is very important, that you can become a global change agent and have no idea that you are doing so. And this is symbolized here with a picture of traffic. Because if you think about it, when we're driving in traffic, it's really, first of all, it's a pretty remarkable system, the fact that it works so well, and there are, relatively so few accidents, that the system works really well. And it works really well because each individual car is driven by a person with agency. And we're really quite good at operating on that level. Think about everything you do kind of unconsciously when you're driving, because we've trained ourselves. You hit the brakes when you need to, you adjust the steering when you need to, and you respond to threats by changing your behavior, and the system as a whole works really well. So there's agency at that individual level, but then we can look at the entire system and we can ask the question, who is driving the global transportation system? And the honest answer is nobody, really. And so it's an example of a system that we all participate in as individuals, and yet nobody has control over it. That's what I mean by inadvertent change. And that's to me what characterizes the beginning of the Anthropocene, the beginning of this phase of human change, when at first you have no idea you're causing global change. And you can think of this on the level of cognitive development of an individual. You think of a child who has not yet developed situational awareness. So they're not really aware of their power in the world, and that makes them more dangerous. Okay, just an illustration. Imagine a kid going into a store with a big backpack, and they're not really aware of their sort of parameters of themselves, and they get excited and turn around to grab something off a shelf, and the backpack knocks over another shelf. You know, when we say this kid has not yet developed situational awareness, and that is, I think, sort of as a global phenomenon, the sort of cognitive level that humanity is largely at now. And this is what I call the Anthropocene dilemma. When your scale of action exceeds your scale of awareness, it's inherently unstable and inherently a little bit dangerous. And some obvious examples of global changes of the third kind, or planetary changes of the third kind. Well, the most obvious example, of course, right now is climate change. And over on the left here, you see the famous Keeling curve, where alarmingly carbon dioxide has been going up every year since we started monitoring it continuously in the late 1950s. You see the little seasonal zigzag, but the overall progression is clear and alarming. And then we're all pretty familiar with the effects of that, so I won't belabor them now. But in the middle, you see, you know, a NASA inspired or NASA derived global model where you can see the sources and sinks of CO2. And so we know a lot about the cycle and where it's coming from and where it's going. And then over on the bottom right, you can see one of the many alarming results of this increase, where the decline of the seasonal sea ice. And there are many more aspects to this that you've all heard about. But in the context of this talk, I merely want to point out that that climate change is an excellent example of this sort of inadvertent level of planetary change, where our sort of cleverness in creating local solutions has exceeded our wisdom in recognizing global consequences. And now, and so another example of inadvertent change, of course, as you've heard about, is the ozone hole, which here in this graph you see in the upper left. It was discovered in the 1970s that we were destroying ozone, and then the problem started to worsen because these chemicals which we had developed, these chlorofluorocarbons, which seemed perfectly safe. In fact, they were sold as environmentally friendly replacements for the more caustic refrigerants that they were replaced, and they are remarkably safe down here in the troposphere where we live. But this is a great example of unintended consequences, because when these chlorofluorocarbons leak up into the stratosphere, which they will eventually when you start introducing them in large amounts in our environment, up in the stratosphere, they interact with ultraviolet light, which knocks off chlorine atoms from one of the C's and the CFCs, knocks off the chlorines, and then those chlorines start destroying ozone. So up in the stratosphere, they're anything but environmentally safe. And you know, it just shows you can't anticipate every consequence of introducing something new into the environment. So you can see here the ozone hole deepens and deepens, but then it starts to stabilize. And the actual story of this ozone hole is a real hopeful one, because what happened was the major industrial countries of the world came together and recognized this was a problem. And, you know, the scientists sounded the alarm, the politicians started talking about it. There was a lot of debate and a lot of denial, and people claimed that it was a hoax, all the same stuff that's happened with climate change. But eventually, the major actors got spooked enough and recognized this was real, so that they came to a global agreement, the Montreal Protocol. And the good news is that it's actually worked, not perfectly, but it's holding. The ozone hole is healing. It's a success story. So this is an example of planetary changes of the third kind, inadvertent changes, but it's also the example I want to introduce now to to introduce planetary changes of the fourth kind, which I call intentional global changes.